right, so for this last section here, day 3 of 12.1, or the part B of today for this lesson, we're going to talk about estimating limits graphically again, but we're going to look at some specific application problems, and then from there you will have some practice. So for these application problems, what I want you to think about is this is where that math really comes alive. With the problems like these, people use limits all of the time, but maybe not with the specific notation that we do in math class, but we use this idea of trends and behavior all the time, and we're going to look at some later today that are taken directly from the current news. And so these trends and being able to describe what's happening at points or as time goes on, this is a really important skill, not just in math, but this is a very real world application. So here we're going to just go through a couple problems so you can see what it looks like, what it happens to interpret the context, and then we'll go from there. So number 1 says this: the concentration in milligrams per milliliter of a certain medicine in a patient's bloodstream T hours after the medicine has been given is given by C of T equals 2.1 T times e to the negative 0.18 T. So that function there, if we plug in a specific time, will give us a concentration. And so it's saying if exist, estimate and interpret the limit as T goes to infinity of this concentration function. So we have only been working with graphs. So let's put this function into our graph. And I have been using Desmos for these just because it's really interactive. You can use a graphing calculator just fine. We just need to see the graph of it. So we want to be careful we type all of this in correctly. So this is 2.1 times, and we're going to use x in place of t. So whenever you could probably use t on Desmos. I actually haven't tried that before. You could just grab the t under ABC and use that, but whenever we're talking about this variable that goes into a function, x stands for that. So 2.1 x times, and then remember that we need to do e under the alphabet, raised to the negative 0.18x. I'm going to close the window, go back home. All right. Oh, this is an interesting function. Okay, so a couple things to remember that in the context of this problem, just as we look at this, is that the time's going to start at 0. We can't have a negative time, or we're not going to go back to before you put the medicine in. So for all practical purposes, this problem starts at 0. So if we look at the concentration, it looks like, as they said, times an hour. So after 1 hour, it's increasing. 2 hours, it's increasing. 3 hours, we're starting to level off, but we're still going up. And it looks like somewhere around 5 hours, 6 hours is where we hit the peak blood concentration of this. And then from here, this is what we care about. We want to estimate the limit as t goes to infinity. So as time goes on, what is the concentration doing? So as we look at this, we can zoom out and look at the right side. It starts leveling off, and the further and further we go, and this would make sense, the more, if you put something in your body's going to use it, it's going to process it, it's going to go through, and over time, it's going to slowly get rid of it at a certain rate. And so then now, we can see here that the concentration, that line pretty much starts overlapping with our x-axis, meaning it is going to 0. So this means for us here that the limit as t goes to infinity of our function c of t, our concentration function, is equal to 0, which means that as time goes on, the concentration of the medicine goes to 0, meaning the medicine is leaving the bloodstream. There is absolutely no one way to say that. If something other some other way to think about it makes more sense to you, but that's my way of thinking about it. That as time goes on, the concentration of the medicine is going to zero. This means that the medicine is being filtered out of or being processed out of the bloodstream and will not be present after, as time goes on, the medicine won't be present anymore. For problem two, wait a second. Okay. For problem two, it says the typical voltage V supplied by an electrical outlet in the United States can be modeled by the function V of t equals 165 sine of 120 pi t, where t is the time in seconds. If it exists, estimate and interpret the limit as t goes to infinity of V of t. So one thing just to point out as we anticipate this is yesterday we saw that the oscillating functions that did not have limits often had trig functions in them. So that's just sort of something to anticipate as we look at this. And so this is saying this function models the voltage that's coming through electrical outlets every second. So let's go ahead and graph this. So I have put this in 160 times 165 times sine of 120 pi x. It took me some playing around. When you first put it in, if you're on a standard home window, it's just going to look red and it's going to look overwhelming. Here's what I did. I clicked the wrench and I originally went from negative 200. You could maybe zoom to negative 300. For the y-axis on the bottom, and then for the x-axis, I could tell it was really small, so I went in like negative 1 to 1, and then I just kind of shrunk it from here. And so this is our function. We can see that it looks kind of like a spring. It's oscillating back and forth, and it is going back and forth between negative 165 and positive 165. And as we keep going, it's doing the exact same thing. So I could scroll like this forever toward positive infinity, but it's going to keep oscillating. And so what that concludes for us here is that this limit doesn't exist because it's oscillating. And so then what we would say is that the limit as t goes to infinity of v of t does not exist because the function oscillates. So because the function oscillates, and it oscillates between negative 165 and positive 165. So it's been a while since I have taken any class that dealt with voltage, but from my common understanding, it does kind of surge back and forth between like a negative and a positive surge of voltage pretty frequently. So it's kind of constantly running through. All right, problem 3. In biology class, a small population of fruit flies is placed in an open container with a piece of fruit and a yeast plant. Delicious. The population after t days is given by p of t equals 230 divided by 1 plus 56.5 e to the negative 0.37 t. If it exists, estimate and interpret the limit as time goes to infinity. All right, so first off, we need to put in our function. So this is 230 divided by 1 plus 56.5 e raised to the negative 0.37x. Oops, I missed the x there. Negative 0.37x. Alrighty, so then let's go home again. Now, because hopefully we can use a nice normal window. And let's zoom out and see what happens. So it looks like this function is growing upwards. It's growing upwards. You want to make sure that we zoom all the way out to see what happens because this is really interesting. So from about time is 0 to maybe like somewhere around 20. I'm going to shrink this so we can see it in our window. There we go. Yeah, somewhere around 20. It's growing, it's growing, it's growing. But if we are not careful and zoom all the way out and fit our graph, and we're going to miss the fact that it levels off right at 230 pretty exactly. And then it keeps going from here. And this is a really common real world model of when things spike and then they level off, which we're about to talk about. There's a lot of that going on right now with coronavirus, where we've had a huge spike and we want it to flatten. And actually, we don't want it to just level and stay. We really want it to then decrease and go back down to zero from there. All right, so here's what we found. For this one, our limit as t goes to infinity of p of t is equal to 230. And to interpret this in a real world context, we could say something like, as time passes. That's a really good way in real world language to talk about t going to infinity. So as time passes, as time goes on, the population will reach a maximum of 230 fruit flies. Awesome. So that means pretty much the population can only sustain 230 fruit flies. All right. For this last one, we've got so much data right now that is going on from COVID-19 that we can use and that we can understand. And this, in terms of limits, finding a specific graph, they kind of all do different things. And I wanted one to be clear, for example. So I looked through, I've been reading the New York Times a fair amount just to stay educated. And this graph I pulled this directly from the New York Times, comparing total number of tests as of March 26th that have been done in the United States compared to Italy and compared to South Korea, which were the places that had done the two topmost tests before the United States, because the US numbers wise surpassed these countries, and that was why we had this news article. And so we're going to do some limits at points using the graph, and these are all going to be estimates because the graph doesn't have super exact values, but we'll do our best. And then we're going to use these graphs to predict some infinite limits, even though we don't quite have them, and then go from there. So I'm going to say U of t represents the US's graph, K of t is South Korea's graph, and I of t is Italy's graph. So first question, part A, use the graph to estimate the limit as t goes to 20 of U of t. Well, first, let's look at this. So here's our graph. So the bluish green is the US, and then the gray has South Korea, and it has Italy. So at 20, we're going to say 20 would be March 20th. How many tests had the US done? So that's going to be this point right about here. And I would say that's just under 150. It looks like it's just under halfway. So we could say that maybe the limit as t goes to 20, it passes through, and it looks like would be approximately 140. And then this is in the thousands. They have done approximately 140,000 tests. And on March 20th, at that point, Italy had done a little bit over 200,000, and South Korea had done over 300,000. And then you can see how it rapidly grows and passes this. So let's use the graph to estimate the limit as t goes to 26. So March 26th of K of t, South Korea's graph. It looks like we're going to be somewhere between 300,000 and 400,000 tests, and slightly above 350. So maybe we could say that's like approximately, and you might think it's a different approximate. I'm going to say maybe that's approximately 365,000 tests. And if we compare, that same day, the US had done near to 600,000 tests, which is kind of crazy. Okay, so now, obviously, this graph stops here, but let's say that we really didn't know much about the situation. Let's say that all we had was this graph. We're going to think about, as time passes, use this graph to predict the behavior, the direction that this is going to go. So for using the trend for the graph of South Korea's testing numbers, using this to look at the limit as time passes, as time goes to infinity, I would say that we're seeing a pretty good leveling off trend. And I would say that it looks like it would probably level off, looking at this rate somewhere around 4,000. It might be, maybe it might pass a little bit over. And obviously this is old data. We're well into April, so it'd be interesting to look at and see this from here. But currently, based off of this, if I was just predicting, I would probably predict that this limit's going to level off. I would predict that maybe the limit as time passes for South Korea's graph, K of T, would equal maybe approximately 400,000 tests. And the idea is that we kind of want it to level off. We like the idea that as time passes, we're going to have to add less and less and less tests each day. And so the total tests we've done will eventually hit a number and it will stay pretty constant at that number. That is what we're looking for. We're looking for a limit that levels off. If I were to look and just not have any context of what's going on and look at the graph of the US, this graph is rapidly going upwards. It's got that exponential curve. And so if I was just thinking mathematically, this looks like the number's just going to keep growing. It's just going to keep getting larger and larger, and it will go, what we could say, to infinity. So then based on this prediction, I would say it's a valid prediction to use the graph alone to say the limit as time goes to infinity, as time passes, of u of t is equal to infinity. That we would do a massive number of tests. They're not bounded. They're just growing every day. They're getting larger and larger. And so we've already talked a little bit about South Korea's graph, that 400 tests, it seems about, if things, I believe, from my understanding, have drastically slowed down in South Korea in terms of the virus growing, so the test amount leveling off at a value would make sense. That would seem realistic. Now, for the US, this graph, just at the trend, this is why we want to flatten curves. We don't want to have to keep doing an exponential amount of tests, adding more and more each day. And so I would say eventually this is going to slow down. And so saying this limit is going to infinity, it's just going to kind of grow out of control, is hopefully, in the public health view of things, not a realistic limit. Because one, it's not sustainable. And two, eventually we will hit a limit. If, let's even say, everyone got tested, we will reach a limit of a cap at some point of how many people that we could possibly test. So hopefully this was interesting to you to kind of think about how limits might be helpful, how trends could be helpful in a very real world context. There's a lot of great data out there. If you're ever interested to talk through any of it with me, I would gladly do that with you. This fourth example is one that I would like you to try, and I would like you to work through on your own. And then as you look at the key, the answers are on there and you can check those from there. And then next up, we've got the 12.1 day 3